Welcome to the crazy, mixed-up world of the atom. So let's start at the beginning. I just want to try and give you a sense of just how ridiculously tiny atoms are. So have a look at these grains of sand on my finger. Now they're pretty small. Each one's about 1/10 of a millimetre across. And yet each one of those grains of sand contains 1 billion trillion atoms. Just try and imagine that, 1 billion trillion atoms. And if I was to expand one of those grains of sand, so let's say it was the size of this beach, about 1 kilometre or so across, you would just about make out the individual atoms, and they'd look like one of those grains of sand. Atoms are very small. But even though atoms are so small, we know a remarkable amount about them. For instance, we even know how many atoms there are in the entire universe, give or take 1 or 2. And given the enormity of the universe and the minuteness of the atom, it's an incredibly big number. It's 1 followed by over 80 zeros. That's 100 million trillion 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 atoms. That's an unimaginably big number. To get a sense of it, compare it to this other unimaginable number, the number of single seconds since the beginning of the universe. That's only a few 100,000 trillion, so you're still short by a factor of 1,000 trillion, 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 trillion. Okay, so we know that atoms are really, really tiny, and we know there's lots of them. That's all fine and dandy. But here's the really weird thing. They're almost completely empty. Have a little look at this. Okay, go, go, go! Now, you may remember from your school physics that the atom is made up of several different parts. So you've got your hard nucleus in the middle, which is played by Louise there on the pink moped. And whizzing around that, you've got the electrons, which are the little light bits. Now that all looks nice, but it turns out that that scale is completely wrong, because if the nucleus was the size of Louise, those electrons would be 50 kilometres away, and they'd weigh about 3 grams, which is the size of this little pebble. Atoms are almost completely empty. Let me explain this another way.
If you could somehow remove that empty space from an atom, it would be impossibly tiny. In fact, if you removed all the empty space from all the atoms of all the people on Earth, you could reduce the entire human population, all 6.8 billion of us, to the size of this apple, or this pasty.
The fact that atoms are empty may feel weird, but that's actually just the beginning. As scientists found out more and more about atoms, they discovered to their own discomfort that they were weirder and more contradictory than they had ever imagined. So they came up with a theory to explain how atoms work, and they called it quantum mechanics. It's so weird that the great physicist Richard Feynman once said, if you think you understand quantum mechanics, you don't understand quantum mechanics. Albert Einstein himself hated it. So, to try and wrap my own brain around this idea, I've come to meet Jim Al-Khalili, master of quantum mechanics, to learn how physicists make sense of the atom.
The best way to visualize atoms is to think of an atom as being like a cloud of possibilities, like it's sort of a fuzzy cloud of atomness spread out over space. And then when you look, you collapse it and force it to make up its mind where it wants to be. So you can never catch it being this fuzzy spread out cloud.
Back on the beach, thanks to quantum mechanics, our simple model of the atom now has to change radically. Jim's cloud of possibility means that all the bits of the atom, the electrons and the nucleus, aren't in a single place. They're in many places at the same time. And they say it's only when we look for them that, pow, they somehow decide where they actually are. But don't worry if this sounds too strange to believe. It freaks out most scientists too. And to show me just how odd quantum mechanics is, Jim wants me to take part in a famous thought experiment in a cupboard.
So, if you close the door.
Yep. All right, Jim, I'm in.
Right, what I didn't tell you, of course, is that sitting above the box is my specially constructed death ray.
No, you failed to mention that.
Now, don't worry too much,
Okay.
but basically quantum mechanics says that an atom can be in two places at once. Now, I've got an atom hooked up so that if it's in one location, it triggers the death ray, which destroys everything inside the box. And if it's in another location, it doesn't trigger the death ray and you'll be fine. You with me?
Okay.
This means that you are now both dead and alive at the same time until I open the box and check whether you're okay. And you're fine.
See, I'm struggling with that still because I mean, I understand the sort of idea behind it in the sort of Lion Witch and the radioactive wardrobe scenario, but clearly I'm alive.
Yeah. Well, the thing is, atoms are doubly sneaky because an atom not only can do two things at once, but it seems that weirdness is restricted down to the level of atoms. So in reality, you are never both dead and alive at the same time because that weirdness of where an atom being in two places at once is constrained down to the level of atoms, and we don't see it in the everyday world.
No, I guess that's the point. I think a lot of people think that it's perhaps some kind of esoteric, spurious notion, but it is in fact the bedrock of modern physics is this.
Yeah. Albert Einstein himself had problems with what quantum mechanics was saying about the world of atoms.
Yeah.
The reason why we put up with this weirdness is that quantum mechanics is the most powerful, the most accurate, the most successful theory in the whole of science. Without it, we wouldn't have most of modern physics, we wouldn't have modern chemistry, we wouldn't have modern electronics, we wouldn't have computers, we wouldn't have the Large Hadron Collider, we wouldn't even know why the sun shines.
So basically, I'm just going to have to accept this and learn to love it.
I think so. I think it's a small price to pay for the most powerful theory in science.